Okay. All right. Let me just stop all this stuff. Okay. So welcome YouTube, Beautiful Mind here. This is going to serve as our lecture for, I think this is week 3 for College Algebra 2, and we're going to be working on section 3.1 exponential functions, right? Okay. It looks kind of like a little bit of a long set, but that's okay. We'll just take our time and do what we need to do. So this is, here we're going to be looking at chapter 3, exponential and logarithmic functions, namely section 3.1 on exponential functions. Some objectives here are that we like to define an exponential function. We like to graph exponential functions, develop formulas for simple and compound interest. We want to understand the number e, graph the natural exponential function, and we'd like to model with exponential functions. So a function f of the form, like this. A function f of the form f of x equals a to the power of x, where a is strictly greater than 0, and a is not equal to 1, is called an exponential function with base a and exponent x. The domain is all rows. So let f of x be these different scenarios. We basically ask to evaluate exponents. For instance, for the first one, let's move this here. So when x is 4, right? So if x is 4, 4 minus 2 is 2. So then 3 squared, so that was going to be 9. I'm going to go ahead and box that. Okay. And then when x is negative 2. So when x is negative 2, here, let's write this one out. So then g of, here, let's write it like this. This is going to be equal to negative 2 times 10 to the power of negative 2. Right? So that's the same as 1 over 10 squared. So that's like 1 over 100. So that's going to be a negative 2 over 100, which reduces down to 1 over 50. Okay. So when x is a negative 3/2, let's write this one out. This is going to be equal to 1 over 9 to the power of a negative 3 over 2, right? So a rational exponent is the same as like is a radical, it's like a square root. So we can do the following. We can do, so since we have 1 over 9, that's the same as 9 to the power of negative 1. A power to another power, we multiply. So that's essentially like a double negative and they cancel each other out. So that's going to be 9 to the power of a positive 3/2, which is the same as the square root of 9 cubed. So then square root of 9 is 3, so that's going to be 27. Okay. Okay. And then 3.2, I would just say use a calculator there. I'm just going to abbreviate it as calculator, and I'm going to rely on my prepared notes for that one. I'm just not going to show those keystrokes. Okay. So you see the 9. I think we got 1 over 50. So, and I think it was negative, right? Yeah. So we just wrote it a different way, but that's okay. I think we got the 27, and then again, use a calculator for that last one. Okay. Moving and grooving. So we're asked to graph this exponential function. So for this one, to introduce the notion of the graphs of exponentials, we're just going to plot points, like choose several values of x and find the corresponding y. Okay. So, for instance, we're going to find our y here. So when x is what, negative 3. So then a negative exponent turns it into a fraction. So there's going to be 1 over 3 cubed. 3 times 3 is 9, times 3 is 27. So that was going to be 1 over 27. When x is negative 2, I think it's going to be 1 over 9, and then 1 over 3. 3 to the power of 0 is 1. 3 to the power of 1 is 3. 3 squared is 9, and then 27. x out of 27. All right. Let's try that one more time. Okay. It's a little off, but it's good. Okay, that's good. Okay. So we got these results. So then we would take the x's and plot the corresponding y's, and we can kind of get a sense of the general shape of an exponential. Let me see, I think we got all these results. So then if we plot those points, you see it kind of makes a shape like this. And this is the general shape of an exponential, where going off to the left, we have a horizontal asymptote in the form of y equals 0, which is the x-axis. And then going off to the right, it grows exponentially like our bank accounts. So then this one, now notice that the base is between 0 and 1, right? So when the base is a half. So let's just find the corresponding, let's choose some x values, find the corresponding y values. So when x is -3, right? So this 1/2 we can rewrite as 2 to the power of -1. So then 2 to the power of -1 to the power of -3 is the same as 2 cubed, right? A power to a power you multiply, then double negative becomes positive. So then 2 cubed, this one is going to be 8. 2 squared is 4. Then 2 to the power of 1 is 2. Anything to the power of 0 is what, 1. And then we get a half, then a quarter, and then an 8. Okay, so what I'm going to do, I'm going to copy this instead of do all of that again right here. Copy. And let's paste. That's not too bad to be a copy. Okay. Okay, that looks good. Okay. All right. So then if we plot all of these ordered pairs, I think we got the same results. 8, 4, 8, 4, 2, 1, 1/2, so on and so on. I think one of my students saw that I was, let me see who it is. Done. Yeah, class is over. I'm gonna have to, I'm gonna have to get them next time because I'm making this right now. Okay, let's keep going. So when we plot those order pairs, we get this graph, right? So notice that this base is between 0 and 1, and we have what's called exponential decay. This is kind of like the same as the previous, but instead of growing exponentially, As we read it left to right, it's decaying exponentially as we read it left to right. So some properties of exponential functions, all right? So when the base is strictly positive and not equal to 1, the domain of an exponential is going to be all reals. The range of an exponential goes from 0 to infinity, the open interval. The entire graph lies above the x-axis, so it never reaches the x-axis, the general shape, right? Since f of x1 over f of x is going to be a to the power of x plus 1 over a, we can rewrite that numerator in this form, right? And then these guys cancel, and at least with just a. So then it says the y values change by a factor of a for each unit increase in x. So every time x increases by 1, the y value increases by a factor of a. When a is strictly larger than 1, we call that a growth factor. The growth factor is a, right? Because the y value is increased by a factor of a for each unit increase in x. The exponential function is an increasing function, so it rises to the right as we go from the left to the right. As x goes off to positive infinity, y goes to positive infinity. As x goes off to negative infinity, y tends to 0, right? That's of the general exponential graph. Then we have the decay factor when that base is between 0 and 1. Because the y value is decreased by a factor of a for each unit increase in x. So for the decay function, f is a decreasing function, so the graph falls to the right. As we move from the left to the right, it goes down. As x goes to negative infinity, y goes to positive infinity. As x goes to positive infinity, y goes to 0. Each exponential function is 1-to-1. That means it has an inverse. So then if we consider two y values, a to the power of m, and if it's equal to a to the power of n, then this implies that m equals n, right? That's a uniqueness property. So that means that f has an inverse. So again, 1-to-1 is synonymous with having an inverse. And we show that it's 1-to-1 with this process, okay? The graph of f of x equals a to the power of x has no x-intercepts, so it never crosses the x-axis. No value of x will cause f of x to equal 0. The graph of f of x is a smooth and continuous curve, and it passes through the points basically when x is -1, 0, and 1, right? So you have these 3 special points. They kind of give you the sense of which way the exponential graph is behaving or moving or whatever. From 4.3 and 4.5.3, we conclude that the x-axis is a horizontal asymptote for every exponential function of this general form, right? The graph of y equals a to the negative x is the reflection about the y-axis, right? So we multiply by a negative inside our base function. So inside manipulations cause a horizontal change, so it causes it to flip over the y-axis, right? So that's from transformations. So then we have this definition. It says the interest rate is the percent charge for the use of the principal for the given period. The interest rate denoted by R is expressed as a decimal. Unless stated otherwise, the period is assumed to be 1 year. That is, R is an annual rate. The amount of interest computed only on the principal is called simple interest. Right? So that's the first form of interest that we're going to introduce. The simple interest I on a principal P at a rate R expressed as a decimal per year for T years is given by this. I equals PRT. This is the simple interest formula. So if you have your formula sheet, you definitely want to add this to your formula sheet, okay? So in this example, Juanita has deposited $8,000 into a bank for 5 years at a simple interest rate of 6%. How much will she receive? How much money will be in her account at the end of 5 years, okay? So if we're doing simple interest, every time we use a formula, write it down. So I equals PRT, right? So then for part A, how much interest will she earn, right? So the interest is going to be P, which is a principal. In this case, it's going to be the 8,000. The rate is 6%. We have to write that as a decimal. So when converting from percents to decimal, The percent symbol, you can kind of look at it like it means per 100, right? So if it's 6%, it's going to be the same as 6 times 1 over 100, right? Or in other words, 6 divided by 100, we move the decimal to the left twice. So if it's 6%, that's going to be 0.06 as a decimal. And it says 5 years, right? So then we just crunch those numbers. Let's see, if that's a 30, so that's the 3, right? 3 times 8 is what, 24? So then that's a 24, 1, 2, 3. 5 years, $24,000, is that right? $6%, yeah, 6% is kind of high. Let's see, that's a 30. Move it twice, wait a minute. I think that's supposed to be 0.03. Because 24 seems kind of high. I'm like, that doesn't seem right. 6 times 5 is 30. Move the decimal twice, so then that's 3. Okay, let me back up. I don't know why I'm getting stuck on this. I'm just trying to do it in my head instead of write it out. 6 times 5 is 30. 0.3. I feel better about that. 20. So instead of 24,000, I think all that we need to do like this. 2,400. That makes more sense, right? Yeah, that makes way more sense. So how much interest will she receive? Should be 2,400, so $2,400. I was like, why does that number? It just didn't feel right. Like, if it were that simple, man, we would be swimming in money. I'm like, something's not right there. And again, I wasn't using a calculator. We could use a calculator to confirm. Let me just confirm these numbers real quick. Hey Siri, what's 8,000 times 0.06 times 5?
8,000 times 0.06 times 5 is 2,400.
Okay. So then if she started with 8,000, and then for part B, her final amount is going to be her principal plus the interest. So that's going to be the 8,000 plus the 2,400. It's going to be 10,400. Okay. So we got 2,400 and 10,400. Okay, let's see how do we do. You see the 2,400 there. You see the 10,400 there. So then next we want to introduce this notion of compound interest. This is going to be the interest paid on both the principal and the accrued or previously earned interest. Interest that is compounded annually is paid once a year. And for the interest compounded annually, the amount owed in the account after 2 years is given by this, right? So we're just going to use this formula. Again, if you have a formula sheet, you would want to add this to your formula sheet. Maybe not this one so much. There's another one that's coming up in just a moment that's a little bit better than this one. When Nita deposited $8,000 to an account at an interest rate of 6%, compounded annually after 5 years. So it says compounded annually, right? So then compound interest formula that we're doing right now. I think it goes like this. The amount equals P times 1 plus R to the power T, okay, right? Let me just make sure P times 1 plus R to the power T, right? Okay, so this is if the interest is compounded annually, like once per year. We're going to extend this a little bit further in just a moment. How much money will she have in her account after 5 years? Okay, so For part A, the amount after 5 years is going to be her principal, which is the 8,000, 1 plus her rate, 6%, so that's going to be 0.06 to the power of 5. Okay, I'm going to try something here. Hey Siri, what's 8,000 times 1.06 times 1.06 times 1.06 times 1.06 times 1.06?
8,000 times 1.06 times 1.06 times 1.06 times 1.06 times 1.06 is about 10,705.8046.
Okay, let me see. So if we round to the nearest cent, we're going to say 80 cents. I think this is what she said. Does this make sense? Now, the reason I did it that way is because sometimes it's kind of difficult to capture like exponents. Like for instance, let me try this. Hey Siri, what's 1.06 to the power of 5 times 8,000?
1.06 to the power of 5 times 8,000 is 10,705.8046 to
Okay.
08.
So that's good to know. Yeah, I just was a little bit hesitant about exponents because sometimes you need parentheses and like it's kind of hard to articulate that. So I was trying to say it in a way where I feel like it could get it. We're gonna go with this, paste. All right. And then for part B, how much interest did she receive? So the interest is going to be what? Her future amount minus the principal. So that number minus 8,000, 2705.80. 2705.80. Okay. 705.80. Let's see how do we do. So for part A, 705.80, you see it there, and 705.80. All right. So now we want to, so again, that last compound interest formula was if we apply the interest once per year. So that's if it's compounded annually. So this is an extension of that previous formula. This is going to be the official compound interest formula. Say we take multiple compoundings per year. So in other words, say we were to apply the interest, like what if we did it twice a year or 3 times or 4 times a year or monthly or daily or whatever? That's where this formula will come in, all right? Where A is going to be the amount after T years, P is the principal, R is the interest rate expressed as a decimal, N is going to be the number of compoundings per year, and then T is going to be the total number of years. Okay. So if $100 is a deposit into a bank account that pays 5% annual interest, find the future value after 1 year if the interest is compounded annually, semi-annually. Okay. So we're using compound interest formula. So again, every time we use a formula, we should write it down. The future amount is going to be P times 1 plus R over N to the power of NT. And again, this guy right here is an R. Somebody's making noise in the hall. My dog can hear her, so she has to bark. Stop. Just lay down. Go back to sleep. Lay down. Lay down. No. No. Stop. 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 She's like, she has to bark if she sees or hears or anything else. I swear she's a true alarm system. Okay, so what I'm gonna do here, I am gonna open up my trusty dusty rusty. See if I can find it. This guy right here. And we need to load it again. I agree. Choose the file. Files. This one. reload, and refresh. Okay, single page.